right, here we go. Final conclusion of 2.6. So this is part 2. We're going to look at two big examples here. This first one we were filling in together. However, after I did this one, I noticed the sound was messed up on the video, so I'm redoing the video, but my work is still there, so that's why you're seeing it filled in. But let's talk through all this stuff. So what we're looking at is making graphs like this, a little more complicated looking, but that's what we're going to be taking a look at. So not a lot to this that's new, right? A lot of this will be things that we've already learned. So they're wanting us to first go through kind of the key features of the graph, which are things like asymptotes and intercepts. And the big reason you want to find those things first is those things are going to help guide us into where we draw these curves. So first thing I want to show you is, as we start looking at these graphs, the graphs are broken up by the vertical asymptotes. So when I see two vertical asymptotes, those two vertical asymptotes create three sections for me to graph in. So there's a section here, there's a section here, and there's a section here. And our job is to figure out where do we draw the curves within those three sections of the grid. And that's where all this extra information comes into play, like intercepts, horizontal asymptotes, things like that. So first things first, we're looking at finding the intercepts right here. So if I want to find the x-intercept, as we already know, I set the y value equal to 0, and then we solve. And something I mentioned in the last video is if I were to solve this equation as it equals 0, the first thing that we would do is take the denominator, multiply it over to the left. It's still 0, right? Because 0 times anything is 0. So really, ultimately, what we're doing is setting the numerator equal to 0 in finding the x-intercept. So if I set x plus 1 equal to 0 and solve it, I'm going to get -1 as my x-intercept. So -1, 0 is the x-intercept. If I plug in a 0 for x, and that's what this means, I'm getting the y-intercept. So if I plug in 0 for x, you can see that I would be left with 1 over -6. And so there's my y-intercept. So I started this graph by just plotting those 2 points. So I had -1, 0 right here, and I have my 0, -1/6 right there. One thing to note, and this is what I tried to mark on my axes, is the scale that they were using. If you look at this, you can see that they were counting by 1s from left to right, but they are counting by 2s on the y-axis. So I marked that so that you could tell where we plot these points and how this is going to look here. Okay, next part of this, if we want to find our vertical asymptotes, we know to set the denominator equal to 0. So if I were to set this equal to 0 and solve it, we would solve it by factoring. So that's why they were asking us to factor the denominator. So if I factor the denominator, set it equal to 0, I can see that my vertical asymptotes are at +3 and -2. Do keep in mind, whenever you write an asymptote, you're writing the equation of a line. So it has to be an equation. You don't just say my vertical asymptotes are at 3 and -2. Right? It's got to be an equation, x equals 3 and x equals -2, because you are writing the equation of those vertical lines that we see on the graph. As soon as you identify those asymptotes, draw them on the graph. Right? Use dotted lines so you can sort of separate out what is the actual graph versus sort of these invisible boundary lines that we're drawing with the asymptotes. The horizontal asymptote, one of the things that we talked about in the last video, we've talked about this multiple times, when the top exponent is smaller than the bottom exponent, we know automatically y equals 0 is the horizontal asymptote. So I tried to draw that one in there as well. That is this dotted line. So now we have all this great information. We're going to do, I would do the rest of this after you graph it. Way easier to identify this information after you've graphed. So let's start looking at the graph. I have the intercepts identified. I have all of my asymptotes identified. So as I look at the three sections of the graph, I have to determine in which location should I draw my curve. Remember, curves always like sort of hug up alongside of those dotted lines, those asymptotes that you've drawn. So when I look at the first section of the graph to the left of my vertical asymptote, I can either draw the curve within those dotted lines right there, or I can draw it within those lines right there. So how did I know to draw it below the x-axis instead of above the x-axis? Well, all I had to do was take a point like -3 and plug it in. So if I took -3, plugged it in for x, in for this guy, I came out with -1/3. So if I just plot that point, -3 and -1/3, so there's the point. So clearly my curve goes through the negative section on the left side here. Okay, so just by plugging in a point, it's going to tell you where that curve is, whether it was up here in the positive zone or down here in the negative zone. Let's do the right side for next instead of the middle. I'll do the middle last. So as I look at the far right side, I did the exact same thing. So I didn't know if I should draw it up here or if I should draw it down here, but by plugging in a point, so I plugged in +4 for x into the original equation, came out with a +5/6. So there's that point. So if my curve has to run through that point, I need to draw this one up into the positive zone right there. So if you go to the middle section, keep in mind that a curve can be on and cross over a horizontal asymptote. That is possible. Your horizontal asymptote is still a guiding line. It's still guided that curve, and it's still guided this curve, but the one in the middle is mainly being guided by the vertical asymptotes, right? And so it's sort of something that we would say sort of breaks one of our rules, but it can happen where you do have a point of the graph on a horizontal asymptote. So that certainly can happen. But again, this curve is really being guided by the vertical asymptotes. So as we look at that, how did I know? There's multiple ways you can draw these curves. It can be an S shape headed downward. It can be an S shape headed upward. It can be a positive U, or it could be a negative U. So how did I know to draw the curve in this direction right here? Well, first of all, we already have 2 points on that curve by finding the intercepts earlier on. So I already knew the curve was going to go through those 2 points. That was a pretty obvious tell right off the bat to draw it this way. How did I know that it would go from here? How did I know that it would go downward instead of back up here and have that U shape? Well, keep in mind, I already found my x-intercept. It was right there. I don't have any other x-intercepts. So this curve cannot come back up this direction because that would create another x-intercept, and we've already found the x-intercepts. There is no other one. So it must have at this point gone downward instead of back up, right? And so that was the easiest way for me to identify where that curve was going to go. So we have to kind of look at all the information that we've already found in order to see where that curve is going to go. And if you're unsure, plug in another point. You could easily take points like 1 or 2, plug them in for x, and you're going to get points down here, right? And that would guide your curve as well. So you can do that too. You can plug in more points, but if you do recognize the information that you've already found and you can use it, then take advantage of that. So let's talk about the limits here. So sorry it's a little unclear on the video. I'm going to try to zoom in. Let me just see if this helps you at all. As I look at the limits, so what they're talking about first is the limit as our graph approaches -2. Why? Because that's a vertical asymptote. So as a graph approaches asymptotes, it takes on a limit, right? So as we approach -2 from the left, so when it says as x approaches -2 from the left, that's a little negative sign right there, which means we're approaching -2 from the left. So as I approach -2 from the left, what is my graph approaching? Well, it's going down and down and down, so it's approaching negative infinity. Right? And so that's why I filled in that one. What about as x approaches negative 2 from the right? So that's a positive sign right there. So as I approach negative 2 from the right side, I can see that my curve is going up and up and up towards positive infinity. And then these two, we're doing the same thing, but now we're approaching the other vertical asymptote at positive 3. Right? So what if we approach positive 3 from the left? So as I approach, so here's me approaching positive 3. So as I approach positive 3 from the left, what is our graph approaching? Negative infinity. And as we approach positive 3 from the right, we're approaching positive infinity. Right? And so that's how we were able to fill those in. And you can see why it's so much better to have the graph done first before you answer questions like this. As far as the domain, we can see that it's everything except negative 2 and positive 3. So that's how we would write it within interval notation. We've already done those before. The range is all real numbers simply because of this middle portion, right? It goes up and down forever. It's continuous within this little zone here. So we know it's all real numbers for the range. As far as continuity goes, a couple ways you could say this. Even though the entire graph is not continuous, right? There's a break here, there's a break here, so it is not continuous everywhere, but within little areas it is continuous. So this graph is continuous everywhere to the left of negative 2. It is continuous everywhere between negative 2 and positive 3. It is also continuous to the right of 3, right? And so here's one way that we could say that it's continuous at all values except at negative 2 and positive 3. Where is it decreasing? Remember how we define decreasing. Decreasing means as x increases, my y values decrease. So in other words, as I move from left to right, the y coordinates are going down and down and down. Now this graph is broken, right? It's not continuous everywhere. So as I have to evaluate this within each portion of the graph. So let's just start with this portion of the graph. That's my puppy barking over here. Within this portion of the graph, I can see that it is decreasing. And if I were to look at the table of values for all of these points, I would see that as my x's get bigger and bigger and bigger, my y values get smaller and smaller and smaller. Hurley, stop, buddy. All right, so we're identifying this portion as a decreasing portion of the graph. Same is going to be true with the other two as well. So on this one, if you were to look at the table of values, from here to here, you would see that as your x's get bigger, your y values get smaller. And so we have this identified as a decreasing, area as well. There we go. And then the same is going to be true with this as well. So you'll notice on this one, they're not even asking for an increasing zone because all three of those are decreasing values within their little areas. Notice on this one, we did not include negative 2 or 3 simply because there is no point on the graph at negative 2 or 3. Those don't exist because of those asymptotes. So that was it for this one. Those are all the main features for this guy. Let's go through the second one. So this one we can completely fill in together. So here's the one other one we're going to look at together. So we're going to fill in all of this as well. So this one will be, it's trying to give you some variation on these. So this one will be just slightly different as we go through it. So just like we did with the other one, we want to start by finding all the key features of the graph, which would mean asymptotes and intercepts. So as we look at finding some intercepts, if we set the numerator equal to 0, that's going to give us our x-intercept, as we already talked about in the last one. So if I said x squared minus 1 equals 0, right, as we solve that, we're going to get positive and negative 1. And you can see as it were factored out right here where those are coming from. So 1 and negative 1. We're getting the x-intercepts. Always good to state those as ordered pairs. I can't quite squeeze that into this little space, but I would write those as 1, 0 and negative 1, 0. And let's just go ahead and plot those. You can see by the scale right here that again they are counting by ones horizontally on the x-axis, but counting by twos on the y-axis. So do keep that in mind. Let's just mark that so we don't forget as we go through. So here was my intercepts that we just found. The y-intercept, as we plug in a 0 for x, you can see that the y-intercept would be 1/9. And again, I would write that as an ordered pair if I had a little more room. So I would write that as 0, 1/9. So that's like right there. That's going to be hard to be too accurate on that, but we'll make it close. At least show that it's in the positive and above the x-axis. So if we factor the denominator, here's where we get the vertical asymptotes. As you set the denominator equal to 0, we can see vertical asymptotes at x equals -3 and at x equals +3. Always good to draw those in as well. 1, 2, 3. So we got all of that information in there. And as far as the horizontal asymptotes goes, since the exponents are equal, I'm just doing the coefficients over each other. So 1 over 1 is 1 for the horizontal. And so you can see it's going to go, I'm going to have a hard time squeezing this in there, but it's somewhere between the 2 and the dot that I got right there. So I'll try to be as accurate as I can on that. So there's my horizontal asymptote. So we can see the zones of this graph taking shape here, right? So I should have a curve somewhere in there. I'm going to have a curve somewhere in here and a curve somewhere in there. So let's keep going through this one. So this is where I would draw the graph before you start identifying all those other pieces of information. And some of those I left already filled in because we went through all of that in the last graph. So as I look at this, how do I know if I should draw the curve here or if I should draw the curve right there? You could plug in points, but if you look at the information that you already know, you don't have to plug in points. We've already found the 2 x-intercepts. There are no other x-intercepts, which means I cannot have a curve in this area. So which means on this one, my curve must be in this area. As you look at the middle piece, this one is super obvious based on the 3 points that we already have, right? Here are the 3 intercepts of the graph. Now, even though we've seen that a graph can cross a horizontal asymptote, I can already see as this one is higher than those 2, it is already showing us the U shape that is taking place right here. So I'm already seeing the U shape taking place. Sorry, it is ugly, but you get the idea. So we can already see, because it goes from here up and then back down, right, that it's not going to then go up again, right? So we wouldn't have that drastic of a curve taking place. And if you're not sure, like I said, plug in another point. If you plug in a point like 2, you're going to get a y value that's down here, and that would also help you guide that curve. So you can always plug in more points if you're not sure. So let's look at the one to the right. And again, what we've already talked about with this curve is I don't have any other x-intercepts, so my curve must be up here instead of down below. Because if I drew it down below, at some point, it's going to cross that x-axis again. And we already know that's not going to happen. So there's my curve. So let's talk about something that we did not talk about in the last one. So let's talk about symmetry with respect to the axes or the origin. Right? So as I look at this, I can tell based on the graph and based on what I see here that this is an even function. It is clearly symmetric to the y-axis. And here's how you would know. I could tell based on this because if I replace those x's with negative x, nothing would change. right? Negative x squared is still positive x squared. Same thing down here. So I could tell just by plugging negative x in for x that nothing would change, and that makes it even, which means it's symmetric to the y-axis. But now that I've graphed it, I can tell by looking at the graph that it is symmetric to the y-axis. If I were to fold my paper along this line, I would be laying the graph right on top of itself, right? And so just visually I can see that it's also symmetric to the y-axis. As far as a local maximum, I can see right here that I have a local maximum because it peaked at that point. It goes down on either side of it. So we have a local maximum of negative, so what do we say that was? Positive 1/9. Remember, a maximum or a minimum is a y value. So where x equals 0, I have a maximum of 1/9. All right, the asymptotes we've already identified. Let's try some end behavior, and we'll call it a day. So as my graph goes on forever to the left and to the right, so now it's saying what's the limit of your function as x approaches positive infinity. In other words, as I go forever to the right, what is my graph approaching? And I can see it's approaching that dotted line, which is my horizontal asymptote at positive 1. And it's doing the same thing to the left. As I go forever towards negative infinity, my graph again is approaching the dotted line, which is at positive 1. So that should be putting it all together for us. So that is the end of 2.6.